Okay, last thing, we're going to learn about box plots and how to construct them. We will construct box plots for the rest of the year. Box plots are the easiest, in my opinion, to make, and the calculator will make them for you. So I'm going to show you how. Easy to make. It also shows the outliers. So if you're looking at a histogram, a dot plot, stem and leaf, you can look at it. You aren't able to determine if there is an outlier or not by only looking at the graph. With a box plot, you can. It'll be a little dot, and it'll tell you that it's an outlier. If you look at the other graphs, you'd have to calculate it by hand and see. So it's not subjective, meaning like you don't have to pick the intervals or anything like that. So it's all box plots will look the same. So AP tests use box plots a lot because when they're grading, everybody's is going to look the same. If they're grading a histogram or a stem and leaf, your answer might be different than your neighbor's, and they would be the same. They could both be correct, but AP tests don't like that because it's harder and it takes longer to grade. You have to have data sets that are larger than 10, otherwise a box plot will not work. So if you have anything less than 10, you're going to use a dot plot. And it's easy for comparative displays. So if you had 2 or 3 or 4 sets of data, it's really easy to make a stack, to stack them. So you'll stack the box plots vertically. So you use it when you have univariate numerical data, but you can have multiple samples, but you're only one variable. I'm going to skip this. A skeleton box plot you won't use, and I'll show you which one on the calculator. The skeleton does not show the outliers. So we will not do a skeleton box plot. We'll use what we call a modified. So I'm just going to put a cross through this because skeleton does not show outliers. So we never construct them. It sounds like one, doesn't it? You will cuss on box plots. You'll cuss on them. Yes. So what I want us to do is in your calculator, I want you to put this data into your calculator.
Okay.
You're killing us.
Put it in your L1. From here, there's a couple things you could do. You can get your 5-number summary by doing stat, calc,
One variable.
and enter. Leave this as list 1.
List 1.
You're right. Thank you. I was going to make that mistake, so thank you. Hit calculate, and when you scroll down, it gives you your minimum, your Q1, your median, Q3, and max. Now, you do need those to draw your box plot. However, if you go to, so everyone do this with me, second, y equals.
Where's that? What?
Y equals is up here. If you're looking at the screen.
Oh.
Everyone should be doing this. Stop talking. Plot 1 should be turned on, so hit enter. Now the type is going to be the 4th. You have to hit the right button. It won't let you hit the down button. So it's, I think that it's the bottom left if you have an older version. If you have the colored one, and it's right.
The 5th one is skeleton.
The 5th one is the skeleton. We don't use it. You want the one with a little dot on it.
I can change the graph. Do I don't mind?
Change your X list to L1. So second 1.
Frequency?
No frequency. Keep it as 1.
No.
Mark, I'm gonna keep the same mark. We'll have to change it.
From here, Wiser talking. From here, zoom 9. Zoom 9 is zoom stat. So zoom 9.
Hit zoom, but it didn't work.
Whoa! Didn't do anything.
Zoom 9 and
It made me a box.
Then hit second quit and then do zoom 9.
What color do I want mine?
Second quit. I don't know what it just gave me this.
I got you. Where's second quit?
This has to be a joke.
Hey, what color should mine be exactly? Light blue, yellow, white, light blue.
Okay, is everyone here?
What are you doing with my box plot?
So from here, you can find your 5-number summary by hitting trace. Trace is going to give you your minimum, your Q1, your median, your Q3. I'm going to talk about this number in a minute, and your maximum. So it gives you those. You don't have to do stat calc enter. From here, you can calculate your range. You can calculate your IQR. You can calculate, it gives you the 5-number summary. So if I wanted to calculate my range, you're going to go all the way out to the outlier. So your range is still your max minus your min. So what would my range be
30.
in this case? 30, because I'm going to take 47 minus 17.
Dang.
My IQR, I'm going to take my Q3 minus my Q1. So what's my Q3?
6.
What's Q3?
30 minus 24.
30.
30 minus 24, which gives me 6. So I can look at the graph and decide that. This number right here is 38, and it just is labeled X in your calculator, like X equals 38. So I'm going to talk about what that means here in a second, okay? Yes? You might have typed in something. Yeah, that's what Donovan had too, so you might have typed in something wrong.
What did we just
Skew his data.
Okay, are we good with making a box plot? So that number that was on the box plot, that was 38. It is because that 47 was an outlier. So if I'm going to redraw it,
Oh, that's your trim.
this is my, no, not trimmed. You've got 47 here, 17, 24, 30, 38. What was the median? 27? 26. Okay, so here is what my box plot would look like. If you were drawing this on a test, it could look like this. The context was population with a bachelor's or higher degree. Percentage. Something like that. For 50 states. So this would be what my box plot would look like. I would accept this if you just label each number. So label your Q1, your Q3, your median, max, min.
Do we need to
Label all of that.
IQR?
No. So here's what my box plot is. Now, how I know this 47 is an outlier. So if you don't have all of your data, then it could say, is this number an outlier, yes or no? These two formulas will calculate what the imaginary fence is that considers it to be an outlier. So if I were to take my data that I just had, Q1 minus 1.5 IQR. So that would be 24 minus 1.5 times 6. Someone put that in your calc. You have to memorize these. The second one would be 30 plus 1.5 times 6. So tell me what these two numbers are.
15 and 39.
15 and 39. Okay, those two numbers, what they represent are, if I have data that is less than 15 or greater than 39, these are my invisible fences. Anything, if I have data outside of those, they become an outlier. So anything to the left or right of those two numbers become an outlier. So that is why 47 is an outlier. From there, your whiskers, because you got your box that goes from Q1 to Q3, your whiskers will stretch out as far inside the invisible fence as the data points that you have. So the most common mistake I see people make is they want to take their whisker and they want to draw it all the way out to 39 and then stop. But look at your original data. Do I have a 39 on there? No, I do not. So inside the fence of 39, the closest number I have is 38. So you draw your whisker as far as you can that's not considered an outlier to the data point in your original data. So that is 38. So that's what this number represents, is it is a whisker that goes all the way out but it stops at 38, then 47 is an outlier. Yes?
Do we always multiply negative or like 1.5 times 6?
Times your IQR.
Oh.
So these two formulas are the formulas to calculate an outlier. Anything outside of those become outliers. Yes?
If you have multiple outliers, there's multiple.
So if I had an 83, it would also be, if I had a 30, or if I had a 40, it would be an outlier. So you put as many dots as you have outliers.
And so all x equals 38 means is that that's your last data point before the outlier point.
It's your last data point before your outlier point. From here, I can also look at shape. So if I've got outliers on the upper end, what kind of shape is this?
Skewed right.
Skewed right. Perfect.
Oh, good.
So here's we did this. If I were to describe, here's my cussing right here. I could say that it's a right skew. It has an outlier at 47, the median 26%, the range of 30%. So I've got my center, which is median. I've got my unusual, my outliers, U. My spread is range. And my shape is positive skew or right skew. So center. No, it could be symmetrical. So next slide. Here are 3 examples of symmetrical box plots. So one of the, I guess, biggest downfalls is that the shape when they're symmetrical, these are 3 different distributions. They both kind of look similar in a box plot.
They do.
The only thing that is different is this box, I guess compared to this one, is that the third box is a little wider than the top one. Why do you think that is?
There's more numbers towards the ends.
So the standard deviation tells me that this one's going to have a larger standard deviation. So if you have a larger standard deviation, you're going to have a wider box.
So a box plot doesn't tell you what the standard deviation is.
No. Smaller standard deviation is going to have a smaller box.
Would it change if it was multimodal box plot? Would it change anything?
It probably would.
Like, what would it look like?
It depends on the data set.
Okay.
One thing that I do also want to talk about that is a big misconception. Guys, stop. A big misconception that I see a lot of people make is that they don't realize that at each quartile, it is containing 25% of the data. So I'm going to go back to the box plot we had here. If I have 51 data points, 25% of them are going to be from the minimum to the Q1. So what's 51 divided by 4? A fourth of them. Yeah, like 12.
12.75.
So about 13 people are from 17 to 24. About 13 people are between 24 and 26. About 14 people from 26 to 30. And then about 14 people from 30 to 47. So 25% of your data are in between each quartile. So your minimum is at the 0 percentile. Your Q1's at the 25th percentile, 50th percentile, 75th percentile. So when you're thinking about the amount of data, then it is the amount of people.
What about outliers? So it goes to the line?
Yeah, so there's a wider range of people in your upper quartile. That's why it is a right skew. Here are some skewed box plots. You're reading it, you go all the way to the outlier. So remember, when you're determining the shape, go to the outlier. The outlier is included in your shape. Some people just want to look at the box and whiskers and forget the shape. So they say it's a symmetrical when really it's a right skew.
So it just matters where the box is on the line.
Mm-hmm.
So if the medium looks like exactly in the middle, it's a symmetrical one.
If it's in the middle and your whiskers are symmetrical.
So for
But like if I had, let me go back. If I had an outlier right here for this data set, this would automatically make it a right skew.
The whiskers would be.
So you start at your median, and I usually draw an arrow to the outside.
So it'd be skewed right.
Yeah, so it'd be a right skew.
Then the other one's approximately symmetrical.
Uh-huh.
It's close, so yeah, I get it.
question.
Yes.
So when you're describing this, do you say the top 25, if there's an outlier like all the way like at 100, would you say the top like 25% is from this to the outlier?
It's all the way to the outlier. So here's some comparative box plots. We're looking at salaries for NBA, and this is probably very dated. It's probably, yeah, it's probably
being paid over $50 million by the Grizzlies.
2009 to 2010. We need some new.
Yes, sir.
So if we wanted to comment on this, comparative cussing, describe the similarities and the differences.
Rudy Gay. In 2010 it was Rudy Gay. What?
Stop. So if I want to compare, I'm going to start with centers. So let's look at comparing all the medians. I'm going to highlight them. And since there are 5 data sets, I'm just going to look at which one has the highest center, which one has the lowest center. So the Knicks have the greatest median. Median salary. And which one has the smallest median salary?
Nuggets.
The Nuggets.
I had a basketball team.
Let's look at the ranges. Which one has the largest range? Lakers, because it goes all the way out here.
It goes away from Robert Sacre.
So Lakers. Who's that outlier probably at this time?
The Grizzlies.
Which one has the smallest range?
Grizzlies.
No, it goes all the way out here.
The Bulls.
Yeah, the Bulls.
No.
2010. Who was on the Bulls in 2010?
Smallest range.
Derrick Rose was a rookie.
Let's go through and name the shapes for all of them. So Bulls, what's the shape for Bulls?
Skewed right.
Right?
Right.
Whoops.
Brownie.
Ooh. What about Lakers, right?
Right.
Knicks, I would say approximately symmetrical.
Grizzlies right.
Grizzlies, right.
Nuggets very right.
Nuggets, right. And then, which ones have outliers? Lakers and Grizzlies have upper outliers.
Grizzlies, Lakers. Nuggets have an overpaid star too.
Yes, sir, Statman.
So I could say Lakers and Grizzlies have upper outliers, and that's how you would comparatively cuss them.
So you don't have to really like compare them when you're trying to median range. You just say this is great.
Yeah.
Like 30 outliers.
As long as you have those words like greatest, lowest, higher, lower, more than, less than, like comparative words. And you're not just listing out the numbers. Yes.
Can you tell if there's like a cluster in there, or do you have
No.
to have the actual data?
No clusters here. You have to have the data. The normal curve. So, how to tell if something is symmetrical or something is normal versus being symmetrical. Because you can look at a data set and say that it's symmetrical, but you don't say that it's normal unless it has these specific qualities. So it needs to be bell-shaped. Whoopsie. There we go. Bell-shaped, unimodal. It's going to be centered at the median. I'm going to skip that. It's going to be centered at the mean, and then it's going to go out a certain number of standard deviations. If you have a larger standard deviation, it's going to be wider and more spread out. If you have a smaller standard deviation, it's going to flatten. It's going to get taller and thinner. So here's my beautiful normal curve. Hello? Here he is. So this is a normal curve. This is the standard normal curve, meaning that it is standard. It's centered at 0 and has standard deviations of 1. So I'm going to draw you a picture best I can. Normal curve will look like this, where it is centered at the mean. Your mean is always your center. So there's two ways that you can do it. You can either have data that has its own mean and standard deviation, and you would put that there. So maybe my mean is 10, my standard deviation is 5. So I'm going to go out 3 standard deviations on each side. So if my standard deviation is 5, then this would be 10, 15, 20, 25. Then it would be 5, 0, negative 5.
That's for normal curve.
This is like if you were given a data set, I gave you a mean and a standard deviation. Or you could convert all of your data to be what we call a standard normal curve, where the center is at 0. I'm going to show you. This is the standard normal curve. So for right now, what I want you to know is that it is centered at your mean. Then it goes out 3 standard deviations. Within your first standard deviation, I think this might be the next slide. It's called the empirical rule. Within your first standard deviation, let me see if it's here. Yeah. Within one standard deviation, it contains 68% of your data. So, if I were to try to apply this to school or something, if the mean GPA was 3.5, or let's just say 3.0, and the standard deviation was 0.2, so let's say that's where my standard deviations are, 0.2. If I go out plus or minus 1 standard deviation from my center, if I surveyed 100 people, then 68 of them would be in between 2.8 and 3.2. So 68% are contained in your first standard deviation, plus or minus 1. 95 are within 2 standard deviations, and 99.7 are within 3 standard deviations. So virtually 99.7% in a normal curve are contained within 3 standard deviations. So when you're drawing a normal curve, you got your mean in the center. I draw out 3 lines. It goes up 3 standard deviations and down 3 standard deviations. So let's do an example. I'm going to show you how to do it by hand, and I'm going to show you how to do it on the calculator. Okay? So here's an example. It says the height of male students, this is at Plano West, is normally, so it has to indicate that it's a normal distribution. It has a mean of 71 and a standard deviation of 2.5. So if I want everyone to draw the normal curve out to the side. Gonna put 71 in the center. Then I'm gonna go up and down 3 standard deviations. So increase by 2.5 would be 73.5, 76, and 78.5. If I go down, 68.5, 66, 63.5. So all I'm doing is adding and subtracting 3 standard deviations. From here, if you want to keep going, you can even draw within one. The 3 numbers you need to have memorized are 68. Need to make a different color. 68, 95, and 99.7. Well, we're about to do some, so thank you for asking. So, what percent of male students are shorter than 66? So, here's my 66 right here. I want to know the percentage less than that. So, based off of I know that 95% are within 2 standard deviations.
So 66 and which?
Not 5%, because that 5% doesn't go all the way up. How much is on the outliers?
So it's 2.5 or something?
0.03 divided by 2, so 0.015. 0.015.
So 1.5%.
So I'm going to take, how much is right here? 2.5?
The whole,
Wait, 2.35 and then 2.5 for the whole thing. Yeah, let's just do it that way. Whoops.
1.5.
So, if it's 95% within 2 standard deviations, each tail is 2.5%. So 2.5, 2.5. So 2.5%. Okay, taller than 68%. If 68 is within 1 standard deviation, how much on the tails? 1 minus 68. 32. Because the whole thing is 100%. So 1 minus 6.68, 32%. And then I'm going to cut that in half. So it would be 16. Between 66 and 73, one of them is 68. How could I figure that out?
95 minus 68.
95 minus 68 divided by 2.
68.
So how much is that?
81.5.
81.5. So that is using your empirical curve. Now, I'm going to show you how to do it in your calculator. Some of you might prefer that, and it works a lot simpler, but I want you to understand the why. So, in your calculator, you're going to hit this so I'm going to exit out of this. Just go to your home screen. Second, vars.
Where's VARs?
Right here. Look at the board. If you don't know what you're doing, look at the screen.
Ms. Thornhill?
Yes, ma'am.
Before the bell rings, would you send Rebecca Bynum out? She'll be leaving.
Yes.
Thanks.
Second vars, you're going to go to normal CDF. Normal, never use normal PDF, and I'll tell you why at a later date, but don't use it. Normal CDF. Now, your lower, upper, stop talking. lower, upper, mean, and standard deviation are all going to be different according to what your data is. So, in my normal curve, depending on the shaded area is your lower and upper bound. So for the first question, it said shorter than 66. So 66 is my upper bound, and I want everything less than that. So I want my lower bound to be negative infinity, which is already there for you, but normally I will write negative 2 to the 99th power, and that kind of takes care of negative infinity for me, if it's not already there for you. This right here is saying negative 1 times 10 to the 99th power, which is pretty big, but I don't usually like making that e because I'm lazy, because you have to hit second and then another number. So my upper bound is then going to be 66. My mean in this problem is 71, and my standard deviation is 2.5.
Paste.
2.5.
This is actually not.
Do we enter on paste?
Do I hit enter once I hit paste?
Yeah. Hit enter.
And hit enter again.
And you should get 0.02275. So the decimals are going to be a little bit different because your calculator is going to be more exact. However, if you use the empirical rule, I will accept both answers because one is approximated and one is exact. So if I were doing this on a free response problem, what I would ask is that you write out exactly what you typed in the calculator along with 4 decimal places. So you would write out normal, CDF, negative infinity, 66, 71, 2.5 equals 0.0228. And this would be your answer. So this right here is showing me your work, and this is showing me your answer. Yes?
Ask for a percentage, do we need to convert it to?
You could.
Put it in the line, do it.
Yeah. So I want you to try the second one. So part B, it says taller than 73.5. So I'm going to go back to normal CDF. And if I'm looking at my normal curve, I want taller than 73.5. So I'm going from 73.5 to infinity. So my lower bound is now 73.5. My upper bound is infinity. My mean and my standard deviation stay the same. And you get point what? 1587
Yes.
How do you make
or
it
1586?
582, just do 10.
Okay.
587.
Then for part C, now we have a lower and an upper bound, so it'll be normal CDF from 66 to 73.5, 71, 2.5.
It's the most exciting thing I've done.
What do you get for that?
0.8186. Boy, am I happy I'm here.
So that is how you do it in the calculator.
Amazing.
Amazing.
Are we always gonna be able to do it?
Yes, you'll always have your calculator.
That's much easier.
You guys have used it.
Yes.
Kelly, you should get that. You're doing
Now, what I mean by converting it to a standard is taking all of those data points and giving them what we call a z-score. A z-score tells you how many standard deviations you are from the mean. So if any of you have taken the SAT, they probably gave you a percentile that you were in. They've standardized all of the data points and put them on a standard normal curve. They gave you a percentile, and every one of you gets a special individual z-score. That tells you how many standard deviations above or below the mean that you are, above the average. If you have a positive z-score, you're above average. If you have a negative z-score, you're below. This formula is needing to be memorized for the rest of the year. I'm going to write it like this: x minus mu over sigma. It's the same thing, it's just written in words above and symbols below. You must memorize.
Is the z-score 0 at 50? What is
Do what?
Okay, so like, you have a negative z-score if you're below the mean.
If you're on the mean, you can have a z-score of 0. Is that what you're asking?
Yeah.
The reason why we standardize things is to, like if you have two different sets of data, they're going to have two different means and two different standard deviations. And putting them on a z-score is like translating all of them to be the same language. It's the best way to compare it. So it's making them both be even on a same playing field where you can compare easily because it's translated well.
What is the value?
Whatever score you made. So we'll look at some of them. So if I were to interpret these z-scores, negative would mean that I'm 2.3 standard deviations below, 1.8 above, 4.3 below. Okay? So here's an example of when you would need a z-score. I've got two different tests where there are two different averages and two different standard deviations. If I want to compare those test grades and see how you did compared to everyone else, you need to find the z-score of both of them. So Sally's taking two different math tests. The mean on score A was a 56 with a standard deviation of 3.5. The mean on test B was a 65 with a standard deviation of 2.8. Sally scored a 62 on test A and a 69 on test B. Which one did she do better? Don't choose the 69 because the score is higher. It's all relative to how everyone else did. Okay, so I want to find the z-score for A and for B. If I'm finding the z-score of test A, I'm going to take her test grade, which was a 62. Going to subtract the mean divided by the standard deviation. So type that in your calculator and tell me what her z-score is. Good. Now I want you to try finding her z-score for test B.
1.429.
So once you have both of her z-scores, which one did she actually do better on?
A.
A, because she has
Z-score is higher.
a higher z-score. Good. So relative to everyone else and how they did, test A must have been higher. So she did better on test A. If you have a multiple choice question and it seems too easy, it's probably because you're not doing the work correctly. So don't just choose the 69. It's usually the opposite because they try to trick you.
I don't want to be trained.
The last thing that we'll talk about is what percentile you are at based on a normal curve. Okay? So everyone is assigned a z-score, and then they're also assigned a percentile. And that just means that you're at or below that percentage. If you're at the 90th percentile, that means that you are better than 90% of your peers. So if we look at this graph right here, what percent of newborn boys had head circumferences greater than 37? Yeah, we're talking about babies' head circumferences.
25.
That should
First
be
thing you measure.
25%.
I wonder how big that boy's head is.
So if this is at the 75th percentile, how much percent was greater than that? How much percent was, that's probably not correct.
25%.
Good.
How much percent was greater? T.
Your homework is to go home and ask your parents what your head circumference was when you were born. 10% of newborn babies have head circumferences bigger than what value?
38.2.
38.2. Good, because I look at the what percentile?
90.
Okay, one last thing I want to do. We learned normal CDF, and that's to find the area under the normal curve. So if I were looking at part A on number 1, it says what percent of babies born had between 43 and 53.5. So that type of question, I would use normal CDF. My lower bound would be 43. My upper bound would be 53.5. My mean is 50, and my standard deviation is 3.5. I want you to answer each question like this, where you're writing out what you type in the calculator.
Do not use
And
PDF.
do not use PDF, you'll get 0. Always. So
Why is it a thing?
I'll tell you about it later when you're more mature.
Do you understand?
Give it a few years.
What do you get?
Listed photos on the calculator.
What does you get for your answer?
81.8.
81%.
Okay. Part B, same kind of thing. Normal CDF, you would do 57 to infinity. But part C, it's now asking for a percentile. So it's giving you the length. And if I have, it never hurts to draw a picture for your data points. So if I've got 50, 3.5, I'm just going out 3 standard deviations.
What percentage of babies are longer than 58 centimeters?
46.5, 43. Okay, so if you draw your normal curve, the next question says a length of 46.5 is at what percentile? So here's my 46.5. It is 1 standard deviation below the mean. There's 2 ways you can find it out. You can either do it by hand. So if my middle value is the 50th percentile, this whole thing is 68, right? From 1 standard deviation away. That means that half of this is how much?
16.
So if I'm going from the mean to the 1 standard deviation away, 34%. So what percentile, if I'm taking the 50th minus the 34th, what percentile would that be at? Not 26, but 16. The 16th percentile. Now, that's how you do it by hand. If I want to use the calculator, I want you to go back to second vars, and I want you to click on the inverse norm. It's M norm. Now, oh, wait, hold on. This is the wrong thing. One way, sorry. One way you could have done this is normal CDF from negative infinity to 46.5. And then 50 and 3.5. Now, if the question said, I'm going to switch this because you'll see a question like this. If the question said, what length of baby is at the 16th percentile? So, does everyone see how I changed the question? I flipped it around, so it's the opposite. What length of baby is at the 16th percentile? That is where
46.5.
That is where I'm giving you the percentile. So they give percentile and they want a value. I'm going to do inverse norm. For area, I'm going to put in that percentile. So I'm going to put in 0.16. Then I'm going to put in the mean and the standard deviation. And tell me what you get. 46.5.
Oh my.
So So when it's the opposite, like it's asked the other way, it gives you the percentile, wants a value, you're going to use inverse norm. If it wants area under the curve, you're going to use normal CDF. Are we okay with that? Those are the only two calculator things you need to know for this kind of question.
Can you explain inverse norm again? Like,
Inverse norm is when it gives you a percentile and it wants you to find a value.